Welcome to my SECOORA Data Challenge project. I am Douglas Cahl at the University of South Carolina. I'm a PhD candidate in oceanography. And the Data Challenge project we're going to be talking about today is eddy identification, tracking, and classification in HF radar surface currents. And before we get started, I think we're just going to cut to a little video of me on the beach. Just doing some repairs in some of the antennas, just so you guys can get a feel for what these radar sites look like. And after that, we're going to go look at the surface current measurements that they produce and how we can go about finding eddies in that data set.
So here we are at our HF radar site in Georgetown, South Carolina. We're repairing some antennas right now. Maybe you can see this one's been hit by some storm damage through one of the hurricanes last year. And these little antennas here you see are measuring the currents that we are using to find where the eddies are. Anyway, I can't wait to tell you more about this project, and we'll see it in action and see where you can get the data and what you can do with the data. And there's data for scientists and other users as well. So we'll talk about that in a second.
So now that you've seen the harsh working conditions I have to do going to the beach in February, we can look at some of the data sets that are required by these HF radar sites. So on the left side here in this figure, these are the surface currents measured by HF radar sites all along the East Coast and Gulf Coast. And if you want to find more of these data sets, SECOORA, follow the SECOORA link, and SECOORA hosts the southeast region of HF radar surface currents. If we look at this little box here, we can zoom in on that. That's right off Cape Hatteras. And we see on the right in the zoomed in feature, we see this anticyclonic or eddy that rotates clockwise. And these eddies are very important features in the ocean. If the eddy was rotating the other way, it would be pulling up cold, nutrient-dense water that would create a fertile fishing ground, excellent for sport fishermen, and they often win tournaments by finding these eddies. Eddies that rotate the other way are also important for mixing and other ocean dynamics that scientists are very interested in. And so what we want to do is we want to be able to identify these eddies in this HF radar data set and classify them. We also want to see how they change through time, right? So these measurements are hourly measurements. So every hour we want to be able to find the eddies, see if it's a continuation of the eddy we found in the previous data set, and see how that changes through time. All right, so the method we're using here was developed by Sadar, Joan, and Post, geometric methods of vortex extraction. Right, and the idea here is that we're just going to create a little streamline. So if we drop a little point here, where would that parcel of water travel with ocean currents like this? Right, it would probably travel in this counterclockwise circle, and we could calculate that it rotated 360 degrees and classify that as an eddy. So from the paper, it's a little complicated. This is some of the math behind the paper, but we're going to kind of explain this in a more simple to understand way. This math is really just pointing to what we can do with our eyes very easily. So on the left side here, we have our radar data set. This is from South Carolina, the two sites we have there. And this is hosted on SECOORA's website, the data set as well. And in the middle here, we have just drawn streamlines. And so what that means is that every point where you see a current here, we just drop a little virtual particle and let the computer figure out where it would go given these currents. And obviously the eddy is very easy to identify visually, right? But now we have to make the computer figure out how to do it automatically. And so the idea here is for each streamline, we're going to calculate how much it rotates, right? And we're going to add up all those angles. And if it comes back close to the starting point and rotates 360 degrees, we're going to classify that as an eddy. So just how your eyes easily pick up this eddy, this mathematical method is, the goal is the same. And so here on the left, we have a zoomed in feature of that eddy. So we've zoomed in on that eddy, and we can see the blue lines here. These are the streamlines that rotate at 360 degrees and are classified as the eddy streamline. The black ellipse here, we fit an ellipse to the shape of that eddy, right? And so this black ellipse signifies the shape that eddy has in the ocean, and the red dot specifies the center of that eddy. Now that we've been able to classify these eddies, identify them, find their shape and their center, we can track it through time. So in the next hour, if that eddy continues, we're going to track it. So on the right side here, we have an eddy track of about 4 days, and we can see that eddy just drifting through our radar coverage area right along this shelf break here. So this is where the Gulf Stream travels, and it's very important for mixing in this region. All right, so here we are with our hourly HF radar data set. If we zoom in down here off the coast of Texas, we see there's this eddy rotational feature here. And so now the code is going to go through the streamline calculation, right? And so you can see now it's starting to draw a streamline, right? So at every one of these points here, there's a vector. It's going to trace out a streamline, try to find out where the eddies are. You can see it's a little slow because of the graphics, but you're starting to find these eddy features, right? And so it's going to keep running through this, and when it identifies streamlines that rotate 360 degrees, it's going to identify them as eddies. So we've now zoomed in a little bit closer, and we're just going to let this code run. So we're not displaying every streamline anymore. We're only going to display the streamlines now that signify eddies. All right, we can see the code now is trying to find these eddies. So each one of these purple lines represents one of these winding streamlines that signifies an eddy, and each one of these little red squares signifies the center of that particular streamline. After this, we're going to fit an ellipse for the shape of the eddy, and we're going to calculate the center of all of these points to signify the center of that eddy. So now that analysis is complete, for this eddy, the blue ellipse is the ellipse fitted to all those streamlines. So the blue ellipse represents the shape of that eddy, and the black X represents the center of that eddy. Analysis has now been completed on the entire eastern seaboard and Gulf Coast, and you can see that there were 4 eddies found in this data set, right? And this was 1 hour of HF radar surface currents. So now we're going to look at where you can get this data. There's an interactive map to use, how you can run this data yourself, and how you can get some of these images. Navigating the main website, I'm going to beautify this a little bit. Basically, there's the interactive map, right, that the Google Maps where you can go look at where the eddies are in the current HF radar data set. You can read about the data. You can download the data. You can look at the code on GitHub and use it yourself, run your own analysis. Right, and there's some switches and settings and optimization you can do, right? So if you're looking for only large eddies or only very small eddies, right, you can modify that code relatively easily. And there's also a video description here as well, right? So it's going to be a YouTube link posted on SECOORA. So if we navigate over to the interactive map, we see Google Maps has loaded up, and it's pulling down the HF radar currents from the national server. So the eddies here are marked in red. So you can see these eddies over in Texas have been identified. So let's go look over here. All right, so we see this large rotational feature in the HF radar currents, and the eddy has been identified by this red ellipse here, right? So that's the shape of the ellipse, right? And if you click on it, there's more information. And so here we get lat, long, ellipse length, right? X and Y. So the major and minor axis sizes for the ellipse are given as well as the rotational angle for the ellipse. So you can use this if you want to plot it yourself. The angular velocity is given in degrees per second. And here it says there is 61 streamlines used in finding this ellipse, right? So this is a measure of how accurate the ellipse is, right? If it was just one streamline, maybe you don't want to include that as an eddy if you're using this for research. And the eddy age is 1 hour, right? And so this code just started running now. But as time passes, if this eddy is present in time, when you click on this, it'll show the eddy path, right? So it'll show the past time history of the eddy. Over here, you can see there's this little tiny ellipse. Oh. And we can see that, yes, there will be some rotation here, right? Looks like a little bit of rotation. And I'm assuming this is just one streamline. Right, so if we click on it, it says only 2 streamlines were used in identifying this ellipse. Right? right? And so that's why the number of streamlines are there. You can also set minimum sizes of the ellipse if you run this yourself. Here's another eddy found over here, right? And if you click on that, it gives you information there. And so you can scroll through this and see where the eddies are, right? And this is updated in real time, so every hour roughly, right? There'll be new data, new HF radar data, and new ellipses identified. All right, so on the website, you can also download the latest data set, right? So that includes all the data analysis. You can look at the code, watch a video description, and a description of the data that you can download is given here, right? So it's a NumPy file. NetCDF had some issues because it's not a standard dimension for all the different time steps. Anyway, this tells you all the different variables, right? And it gives you a description of them. And here's a little example on how you can load that, right? So if you just want to use the analysis that was created here for the East Coast and Gulf Coast, you can just download this file here. There's also a real simple CSV file, so that's just used for the web graphics, right? So it really just has real-time data and path history, nothing else. But the CSV, anybody should get going, right? So you can just grab that, open it in Excel, and jump right in. On the main website, it also links to the GitHub, where you can find all the Python code that was used to create this project, right? And you can run it yourself. There's a master file, and then 3 scripts and a function, right, used here. So the README, I'll be filling that out later. It'll give you instructions on how to run this on your own data set. And the master is pretty short. It's pretty easy to follow. You have some switches and some settings, and it really shouldn't be a problem. So hopefully you guys can get this up and running and run your own data set. So once again, here's the website, douglascahl.com/Eddy, and there'll be a link from the SECOORA website as well. So I hope you find it very useful and enjoy it, and love to hear some good stories from some users that found it useful and helped you for fishing or for research or whatever you want. We should also give thanks to SECOORA for funding this project and hosting the data. And without SECOORA, this project would never have happened. And so they're a really great alliance in this region.